I'll get started now. First, I'd like to acknowledge the traditional owners of the land on which we are meeting, and I pay my respects to the elders past and present and the Aboriginal elders of other communities who may be here today. Good afternoon, everyone. Thank you for joining this month's webinar titled Traffic and Cars. I'm Sabrina Idrose, the Centre for Safe Air Postdoctoral Research Fellow, and I'll be chairing today's webinar. Traffic is a major cause of air pollution-related illness and premature death in Australia. Today's webinar will delve into the latest research and real-world data on how cars contribute to air pollution and what it means for public health and policy. It will feature presentations from Dr. Nicolás Borchers Arriagada and Jason Smith. We also have the pleasure of having Sarah Roberts as a panelist. Each speaker will present for up to 20 minutes, followed by a Q&A after all presentations have ended, so please drop your questions in the Q&A section. Our first speaker is Dr. Nico Borchers Arriagada, who is the Centre for Safe Air Postdoctoral Research Fellow with a background in industrial and environmental engineering, environment, and health sciences. Nico has developed a career as a multidisciplinary data scientist whose work intersects modeling, public health, health economics, bushfire management, and more broadly, risks of climate-related and extreme weather events. During his PhD, he assessed the health burden of bushfire smoke in Australia and is currently working on novel methods to improve and refine population exposure estimates to wood heater smoke and landscape fire smoke PM2.5, assess the health burden of different climate-related extreme events, and the use of health economic and visualization techniques to better communicate policy-related research. Over to you, Nico.
Thanks, Sabrina. Hello, everyone, and thank you for the team for putting this webinar together. I'm just going to share my slides. Is that okay?
Yep.
Okay.
That's great.
Okay. Hello, everyone. So I want to introduce myself. I am a postdoctoral research fellow based at the University of Tasmania. I would like to do a quick acknowledgement of country. So I would like to acknowledge the Tasmanian Aboriginal community as the continuing custodians of Lutruwita, Tasmania, and honor Aboriginal elders past and present. And for today's presentation, I will be based on the analysis from this article that was published in the journal Environmental Research. If you want to access it, you could use the QR code or just look for it. And I would also like to thank and acknowledge my colleagues and co-authors that contributed to this article. So Tim, Jeffrey, Luke, and Faye. This is the outline of the presentation today. So I will start first by showing you a little bit of what we know in relation to the mortality burden of air pollution and traffic-related air pollution in Australia, and why this study was needed. So airborne pollutants pose a huge threat to human health. This figure depicts different pollution sources and pollutants that are emitted from each source. For this presentation, I will mainly focus on two of them, which are fine particulate matter, or PM2.5, and nitrogen dioxide, or NO2. So pollution from PM2.5 and NO2 is associated with multiple health risks, including death. And I'll start with PM2.5, so which is probably the pollutant that poses the greatest threat to human health, or at least the one that has been most widely studied. So PM2.5 can lodge deep into the respiratory tract upon inhalation and trigger respiratory illnesses such as asthma, bronchitis, and emphysema. And it can also enter the bloodstream and travel to the heart, increasing the potential for cardiovascular problems such as arrhythmic heartbeats and heart attacks, and even lead to premature deaths. On the other hand, NO2 is a gas and a precursor for other pollutants such as PM2.5 or ozone. And some common sources include combustion, mainly from, for example, running car engines, or indoor pollution such as gas stoves. And although the epidemiological body of work around NO2 is not as large as that of PM2.5, there are multiple studies that have linked NO2 with a myriad amount of health impacts, ranging from coughing and wheezing to increased risk of premature deaths. In Australia, There's some estimates of the mortality burden attributable to PM2.5 alone, with estimates ranging between 2,600 deaths per year to over 3,200 deaths per year. But there are no published estimates for NO2. There are no published estimates for the combined impact of PM2.5 and NO2 from all sources, and there are no estimates, well, at least before this study, attributable to traffic-related pollution from PM2.5 and NO2. Although there was this gap, previous research can give us some hints on this impact. So for example, there are a few estimates, I'm just showing here two, one from the Bureau of Infrastructure and Transport Research Economics from 2005, and another one led by G.I.G. Lee from UNSW from 2024. And both of these studies estimate between 1,000 to 2,000, roughly, deaths per year for different years, with slightly higher estimates for 2018, although not a huge difference. And both of these studies based their analysis on PM10, which is a particle size that is larger than PM2.5. It would usually include other types of components, such as coarse particles, dust from vehicle exhaust, tire, and brake wear, and the resuspension of road dust caused by vehicle movement, as well as the emissions from PM2.5, which would mainly come from combustion. We also know from other research that on-road mobile sources, so aka vehicles, are an important source to anthropogenic PM2.5. So research led by Richard Broom and published in 2020 estimated that in the Sydney metropolitan region, about 17% of anthropogenic PM2.5 comes from on-road mobile sources. Although this value would probably vary by location, it will likely be higher for highly populated and urbanized settings and lower for others. And finally, there's this study published by one of my co-authors and colleague, Timothy Chaston from the University of Canberra, who studied the impact of COVID-19 mobility restrictions during April 2020 and estimated that if we were to implement interventions equivalent to those COVID-19 mobility restrictions, we could achieve a reduction of about 27% in terms of NO2 emissions and attributable deaths. And he also estimated that about 1%, a bit more, of deaths could be attributable to NO2 exposures in Australian cities. If we extrapolate this number and multiply by the average deaths across Australia, this would equate to just under 2,000 deaths per year from NO2. So we wanted to, knowing these gaps and what was out there, we wanted to find out how many deaths in Australia were caused by air pollution, specifically from traffic, and how PM2.5 and NO2 contributed. And although we did multiple sensitivity analysis varying a lot of the modeling parameters, I will not show them here. I'm happy to talk about those, or for you to read the article and shoot me an email if you're interested. So in general terms, this figure represents how the mortality burden was estimated. So essentially what we have, and we can see here on the top right, we have human activity. It could be non-human, but for the purpose of this study, it was human activity that produces pollutant emissions, mainly from combustion. It could be PM2.5, NO2. And once those pollutants are emitted, they mix with the air, with a large volume of air. And this is when we talk about concentration, which refers to the amount of pollutants that are actually present in the air at a given place and time. And it's usually measured by an amount, normally an amount of mass per volume of air. Then we talk about exposure, which is when we see people that are actually inhaling and absorbing these pollutants. So exposure takes into account not only the concentration that is in the air, but also at a specific location, but also the number of people that live there, work, or are active and are inhaling these pollutants. And epidemiologists have studied how exposure to different pollutants is associated to different health outcomes. And in some cases, as I told you earlier, the evidence is very robust, for example, with PM2.5 and mortality. And what we can do is use these estimates from these epidemiological studies, and we can calculate something called the effect estimate or health risk coefficient, which will be here this beta. And using that beta, we can use this equation to calculate the theoretical impact on human health. So with this equation, we can calculate the number of cases for a particular health outcome. Additionally, for this study, we have a few essential steps that we needed to consider. First of all, is, okay, so we have pollutant emissions and concentrations in the atmosphere, but how can we calculate those that are related only to traffic emissions? Which is not that easy. And then, given the wide range of evidence, it's like, what specific health risk coefficient do we use for this analysis? And also, given that we want to estimate not only PM2.5, but the burden attributable to NO2 as well. So the first one, this is a very rough template of the methods. This is a very simplified version. So what we need to estimate the traffic-related PM2.5 and NO2. And looking at what was available for Australia, we have modeling from chemical transport models, or CTMs, which take into account emissions from different sources and model the concentrations in the atmosphere at very high spatial and temporal resolution. So what we did was we took the results from these two CTM runs, one for the Sydney Greater Metropolitan Region and one for Victoria. And we were able to calculate these two measures, which is the share of PM2.5 concentrations actually related to traffic emissions and the share of NO2 concentrations related to traffic emissions. Once we had this data collated, so I'll be talking also about TRAP maybe, and TRAP means traffic-related air pollution. And be aware that this is only available for Victoria and the Sydney GMR. So we combined this with other spatial predictors that were available, and we developed this machine learning model, specifically a random forest model, to predict the share of PM2.5 and NO2 concentration based on all of these different emissions and population predictors. Once we had this model, the details will be in the article, but once we had this model, we were able to combine with prediction data across all of Australia and calculate this share of PM2.5 and NO2 for all of Australia. So now with this model, we were able to estimate for a specific location, for example, let's say Perth, how much of the PM2.5 concentration in Perth could be associated with traffic emissions. Then coming to our second issue, which is which health risk coefficient do we actually need to use? So I want to talk about something. I hope these next two slides are not that complicated. I tried to simplify it, but in environmental epidemiology, we talk about a single pollutant model when the effect of only one pollutant is considered. So usually what happens is that what's in the atmosphere is not just one pollutant, but it's a complex mixture of pollutants. And some of them might be highly or partially correlated, especially if they come from combustion. So for example, in some cases, ozone may be correlated to PM2.5 or NO2 to PM2.5. So when we talk about a single pollutant model, this is a statistical model that tries to capture the effect of PM2.5 on a health outcome, for example, without adjusting for other partially or more highly correlated pollutants, for example, NO2. And what happens is that this model would yield a result that may partially reflect the effect of NO2, so not only PM2.5, but it also captures a little bit of NO2. If we wanted to capture only the effect of PM2.5, we would talk about a two pollutant model, which is a statistical model where you calculate the effect on PM2.5, but we also adjust for NO2. So in this case, theoretically, the results should not reflect the effect of NO2, but only of PM2.5. the ideal for our analysis would be to use health risk coefficients or betas that come from two pollutant models and have one beta for PM2.5 and another one for NO2. We can do the health burden calculations with the equations I showed before, and then we can sum up these estimates. But the reality is not, it's not that simple. And also, well, with this slide, I want to maybe show this in a different way. So suppose we were to know the true burden associated with PM2.5 and NO2. This is just an example. So let's say 100 deaths. That's the true burden. This is what would happen if we were to use a beta from a single pollutant model and a single pollutant alone. So if we were to use let's say for PM2.5, just a beta for PM2.5 from a single pollutant, we would maybe estimate 60 deaths. And if we were to use one for NO2, it might be, for example, 55 deaths. And if we were to add these two estimates, so remember, it's single pollutant model, we would get 115 deaths, which is an overestimation of the true burden. So we cannot use this approach. And this usually happens, this happens a lot with health impact studies or burden estimates where results are presented for one pollutant or for multiple pollutants, but they're never added. In our case, we wanted to sum them up. So what did we do? So we followed recommendations published by the British Committee on the Medical Effects of Air Pollutants, so COMIAP, which proposed a method that can be used to mutually adjust these betas that come from single pollutant models. You adjust them, and then you can sum them up. Acknowledging also that there are many uncertainties in the estimates and the parameters that you use to model this, we model different scenarios. Here I will just show you results from 6 scenarios, but essentially what we did was on a first scenario, we selected a beta only for PM2.5 from a single pollutant model. It's not from one single pollutant model. These are results that come from meta-analysis. So studies that compiled multiple cohort studies or results from multiple studies, and they calculated a pooled estimate. A second scenario would be a beta from NO2 that would come from only single pollutant models. And then we did 4 scenarios where we used the approach recommended by COMIAP, where we use these mutually adjusted betas and sum the estimates for PM2.5 and NO2. What did we find? So on the left, all of this is just showing the same result, but I'll walk you through a bit. So on the left, we have sort of a forest plot that's showing the results for these 6 scenarios. In the top 6 are from all sources, the bottom 6 from traffic-related air pollution. And they are in the order that I explained earlier. So the first one would be when using a single pollutant beta only for PM2.5, the second one the same only for NO2, and then the next 4 when we use this approach recommended by COMIAP. And what we can see is that across all of Australia, when you use an estimate from a single pollutant model for PM2.5, the estimate here on top, this one, which ranges between about 3,900 and with a range, is very similar to the combined estimate from these 4 calculations, which would be the COMIAP estimate. And in the bottom, what we see is for TRAP, when we use NO2, on the other hand, not PM2.5, but NO2, we get results that are very similar to those when we're using the methods suggested by COMIAP. And here on the right, you can see the values. So we can see that from all sources, our mid-estimate ranges somewhere between about 3,000 deaths per year to just over 4,000 deaths per year. And those for traffic-related air pollution range between about 1,700 deaths per year to just under 2,000 deaths per year. And this forest plot shows sort of the same thing. Each dot will be the mid-estimate from each of these scenarios, and the gray line shows the range of uncertainty across all studies. What's interesting, what we didn't really know, is that from this modeling, it seems that about 51% of the burden related to traffic air pollution, when we consider PM2.5 and NO2, when we consider PM2.5 and NO2, it seems that about half of the burden comes from traffic-related air pollution, which is something that we hadn't seen in other studies that were only looking at PM2.5, for example. As part of this project, we were also developing a visualization dashboard using a platform called Tableau. It's not finished yet, but it can be used potentially to explore the results at different geographical levels with different metrics. So I'll show you just quickly. I have that here. So this is the working version. Here we have the results for all across all of Australia. But for example, if you were to select, not select, but just hover over one of these jurisdictions, well, it's not working now, but you should, what will happen is that it will filter out the results on the table, and you can also select, for example, different state and territories. Sorry. It's not working. Okay, that's why it hasn't been published. Okay, what does this matter? So from these results, we can see now more concretely that traffic-related pollution is a significant public health issue. We also know from previous research that reducing traffic emissions could potentially save thousands of deaths. So for example, Timothy Chasten calculated that if we were to have interventions similar to that would have an impact similar to the COVID-19 mobility restrictions, we could achieve at least 27% reduction in the health burden. So all of this tells us that there is potential for reduction. So cleaner transport means cleaner air, and then it means healthier communities. So it is very likely that we can achieve very good public health benefits without having to impose mobility restrictions like COVID-19, but rather changing the way that we travel. So what next? So the results from this study and many other modeling exercises rely on emission inventories that were developed using theoretical emission factors that try to replicate what is happening in the modeling fleet, in the vehicle fleet. So in this case, this report published from New South Wales, they estimate that this is the trend of the average of the total emissions, NOx tons per year, between 2003 up to 2036. And we can see that it is projected to decline, even though it is very likely that the vehicle kilometers traveled will increase as the populations and the number of vehicles increases. But for our study, we use an estimate of about 1.3 grams of NOx per vehicle kilometer traveled, or 1,300 grams per kilometer traveled. But although the modeling suggests that with technology improvements and vehicle renewal, the total emissions will decline to the future, we're not completely certain about this. No? When we look at average emission factors for the transport sector, from different emissions inventories across years and locations, we can also see a steady decline in the estimates. So this is in theory. But today we also have another speaker with us, Jason Smith, who is the program director of the real world testing program from the Australian Automobile Association. So Jason was telling me that the program has been testing real world emissions and performance of different vehicles for the past 2 years, and has kindly shared some of the data they are producing. And I produced this figure with that data. And this is only to show you, but it's the tip of the iceberg. So we can see this red line shows the average emission factor across the fleet for our study. So 1,300 milligrams per kilometer traveled for NOx. And in blue dots, we can see for the different fuel types that this would be the real world emissions that have been tested on the vehicles that this program is working with, which are way below these estimates. And this opens, so I believe that the use of this data could have great potential to do further analysis and explore different things such as pathways to cleaner transport or studies assessing the cost effectiveness of different emission standards, or it's open to a lot of possibilities now. But Jason can talk a little bit more about this. Thank you, and let's work together to reduce air pollution and protect public health. And sorry again for that interruption.
Thanks, Nico, and no worries at all. Thanks for sharing your fascinating body of work. There are some questions in the chat, but we'll get to them after Jason's presentation. Our next speaker is Jason Smith. Jason is the program director at the Australian Automobile Association's Real World Testing Program. Jason is an engineer having held roles in vehicle testing and vehicle standards, as well as technical policy development on transport issues affecting consumers such as fuel quality, vehicle emissions, and vehicle safety. He's leading the Real World Testing Program, a program funded by the Australian government to provide consumers and car buyers with transparency through better information on the running costs and the environmental performance of new vehicles by testing them in real-world operating conditions. As mentioned, we also have Sarah Roberts joining us as a panelist. Sarah is the Director of Research who leads the Australian Automobile Association's Vehicle Emissions and Advanced Technology Research projects, including aspects of the real-world testing program. With a background in engineering, strategy, and regulatory policy, she has worked extensively across automotive, energy, and transport sectors. Her work helps government, industry, and consumers better understand real-world fuel use and emissions, providing evidence that supports improved policy, cleaner vehicles, and safer roads. Thanks for joining us, Sarah. So now over to you, Jason.
Thank you, Sabrina and Nico. Slide. You can see that fine, Sabrina?
Yep, that's perfect. Thanks, Jason.
Firstly, thank you very much to the Centre for Safe Air for inviting Sarah and I along today. Today we'll talk to you a little bit about the Real World Testing Program, what it does, why it exists, and what it's funding. And then I wanted to touch on a little bit of the data that we've been collecting so far and give you some examples of that. So firstly, who is the Australian Automobile Association? The AAA is the peak body for Australia's 7 state-based motoring clubs and their 9.5 million members. The AAA exists to advocate at a national level on consumer issues impacting transport and mobility. Key issues you'll hear the AAA focus on are safety, affordability, sustainability, equity, transparency, and fairness. And the Real World Testing Program is another arm of the AAA sitting alongside these advocacy activities and core values. So what is the Real World Testing Program? Essentially, the Real World Testing Program, well, it commenced in 2023 and it tests real cars on real roads in Australia using real Australian fuels. And when I say real fuels, I mean that we're using market fuel, not a test specification that real people don't buy in Australia. We do this testing to understand the real world fuel consumption, running costs and environmental performance of new model vehicles, and we publish the results publicly. The program is fully funded by the Commonwealth to test up to 200 cars over 4 years and publish the results to A, inform consumers and new car buyers and the market generally, and B, to provide additional data to governments and support new policy development. And the third aim is to support and inform international standards development. Testing is done independently with the program sourcing real vehicles from the car park. So they're actual cars that people own and operate. We have some conditions around what those cars must look like. And we also only test cars that are available on the new market. So the figures that Nico mentioned before are vehicles reflective of new technology entering the fleet. We do not test older vehicles. Since testing started in August 2023, we've tested 119 vehicles. 114 of those are petrol, diesel, and hybrid vehicles, and we've tested 5 electric vehicles. We've not yet started testing plug-in hybrid electric vehicles, but those are coming soon, and they're essentially the next cab off the rank, if you will. So a quick overview on how the testing works. For context, and I guess it's a bit of a scene setter, some of you might remember the Volkswagen emission scandal of 2015. The European response to this was to implement what's called the Real Driving Emissions Test, or the RDE test, and that was implemented as part of European regulation. This test requires car makers to test their vehicles on real roads using what's called a portable emissions measurement system. And this is now done as part of regulation to demonstrate that the emissions in real world, or the real world performance, are not substantially different to those recorded by the car makers in lab testing. And car makers are already doing this test when providing their vehicles to Europe as part of their certification. So we conduct this same test in Australia using the same portable emissions measurement systems. And these systems, essentially, they measure the gases as they leave the exhaust of the car. We had to make some minor tweaks to the protocol that's used in European regulation, but these tweaks are really around Australianising the test procedure, and they talk to things like the fuel specification, as well as the average speed requirements for highway driving in particular. But the key difference, I guess, between that test done as part of European regulation and the test that we do at the AAA is we do it independently and we publish the results publicly. A quick overview of the test protocol. So the test protocol requires a 1/3 split between urban driving, which is 0 to 60 kilometers an hour, rural driving, which is 60 to 80 kilometers an hour, and 1/3 motorway driving, which is anything above 80 kilometers an hour. The test procedure also, or the protocols, include a series of controls to ensure that tests are realistic and consistent while still being driven in a real world environment. For instance, it specifies the average speeds in each of the 3 segments, so urban, rural, and motorway. If we don't meet that average speed within a tolerance, we have to redo the test. Similarly, there are requirements based on driving style, which is a measurement informed by acceleration. And where these requirements are not met, i.e. the car is driven too aggressively or too leniently, the test is invalid and we have to repeat it. And finally, there is a series of rules around weather conditions. So things like maximum, minimum temperature, rain, wind, etc. So there'll be no tests as part of our program tested in temperatures above 30 degrees. We don't test in heavy rain or wind. That's really just around making sure our results are consistent while still being real world. Where all of those checks and balances that are put in place aren't met, again, the test is invalid and we repeat the test. The other thing that's worth mentioning, and I guess it's depicted on the screen there, we use the exact same test route for every car that we test. It's 93 kilometres long, and it's in and around Geelong in Victoria, and it takes about 1 hour and 45 minutes to complete each time. The development of this route is quite important for our program. We put a lot of time and effort into doing this. It was basically a 6-month piece of work before we started testing, and it needed to make sure that the test route was going to be consistent over the term of the program, over the 4-year term of the program. So there's an example just to, I guess, put it into context. The changing schedules for the Spirit of Tasmania as it arrives in Geelong was one of the reasons why we decided we had to avoid that entire area of Geelong, as the traffic would not be consistent throughout the week and would not meet our repeatability criteria. Each vehicle that we test is tested at least twice across this test route. If these 2 tests do not have a total trip time within 5 minutes of each other and the total CO2 emissions are not within 5% of each other, it fails our repeatability criteria and we trigger more tests. And you can see this on the screen, for internal combustion engine vehicles, we test for fuel consumption, CO2 emissions, oxides of nitrogen, so NO and NO2, carbon monoxide emissions, and solid particle emissions, which we measure by particle number. And for battery electric vehicles, we test energy consumption and electric driving range. I guess the thing to remember about all of those performance measures that we look at is that all of those are figures that are either reported publicly by car makers for consumers, or these are figures that are reported as part of their mandatory emissions testing. Before I get into the results and I guess some of the findings, I quickly wanted to explain why the program exists and who its key audience is. So for the next few minutes, I'll focus a little bit on fuel consumption and CO2 emissions. And I guess the important point there is that the average person has a better understanding of fuel consumption and CO2 emissions as opposed to the tailpipe pollutant emissions. So probably the most important piece of context is the windscreen sticker, which you can see on the screen. This is the sticker that is on the windscreen of all new cars at every dealership. It's a mandatory requirement car makers have to put this sticker on the windscreen, and it's there to show the fuel consumption and CO2 emissions recorded in the car maker's lab testing. It's there to support consumers in informed decision making, but in doing so, it creates a competitive advantage or competitive incentive, sorry, for vehicle brands to lower their fuel consumption and their emissions. The trouble with this lab testing is that the lab test and real world outcomes are not the same. We also know that the underlying lab test is susceptible to optimization, and there's been a growing gap between those lab test results and real world outcomes reported internationally over the last decade or so. So for an everyday consumer, you are essentially tasked with taking that lab result from that windscreen label and determining what that means for you. For an example, imagine two cars, different cars from different car makers, but they both have the same fuel consumption figure reported on the windscreen label. Now, should the consumer expect both of those vehicles to perform the same in the real world? They perform the same in the lab. Why shouldn't they perform the same on the road? And this is really the gap about why the program was funded and why it exists, and the gap that it's trying to plug. It's that gap for consumers in terms of those lab test results and what a real world outcome looks like. The last thing I'll mention on this slide is that as increasing pressure is applied to car makers to reduce their emissions, pressure from both regulation and the consumer demand, there is a real potential for this gap between lab and real-world outcomes to widen. And the program essentially serves to ensure that that does not happen. I'll quickly cover off on a couple of examples, again, just to put it into context. So this is that example that I mentioned before. Both vehicles report the same fuel consumption figure on the windscreen based on lab tests. It's the white box at the left of both of those vehicles. 4 litres per 100 is what both these cars report. They're both small cars and they're both marketed as hybrids. But in our real-world tests, which are shown in the yellow box, the vehicle on the right, the Toyota, used 10% more fuel, while the vehicle on the left used 31% more fuel. So, go back to that question, can you expect two cars with the same lab result to perform the same in the real world? Our testing shows that you cannot. The last thing that I'll show you on fuel consumption, I guess, just to further iterate that point, further emphasize that point, sorry. This chart shows the variation between the on-road fuel consumption that we measure and the lab fuel consumption reported on the windscreen label for every one of the 114 internal combustion engine vehicles we've tested. So there's a result there that's 35. That vehicle used 35% more fuel on road than it did in its lab test. A couple of, I guess, quick stats. 87 of the 114 vehicles tested used more fuel in real driving than it did in its lab test, with the largest variation being 35% more, all the way through to, you can see on the screen, there's a handful of vehicles that use less fuel on road, with one using 13% less fuel. And the important, I guess, thing from this screen, or this slide, is it's different for every model and every engine combination. And this is probably the most important lesson that we've learned to date, and that is that there's no rule of thumb that can help you translate a lab result into a real-world outcome. And this really, I guess, highlights or talks to the limitations of relying on lab tests, because relative comparisons can't be relied upon. I guess an example of that is better performance in the lab doesn't necessarily translate into better performance on the road. Okay, let's move on to some noxious emissions results. So I mentioned before that we test for oxides of nitrogen, carbon monoxide, hydrocarbons, solid particles. Every car that we test, we publish the total trip results for these emissions. So that's the distance-specific results across the entire 93-kilometre journey or trip. On the screen, you can see the results. These are results for a diesel vehicle. This is just an example to highlight the data to you. In the yellow box, the results that we recorded in the real-world tests. And the two results, or two rows above, sorry, the limits applicable to each pollutant in their lab tests. So, for a vehicle to comply with certification, they have to produce lab results that are below these numbers. We've included both the Euro 5 and the Euro 6 limits in there for context. So just looking at these results, this car produced oxides of nitrogen in on-road driving that were about 50% above the current lab limit. Again, some stats. Of the 114 vehicles that we've tested, 36 have produced on-road emissions that were above their applicable lab limits. For diesel vehicles, 17 out of the 24 diesel vehicles produced NOx emissions that were above the lab limits. Interestingly, or perhaps not surprisingly, the remaining 7 vehicles all fuel with a technology that is essentially designed to reduce NOx. It's called selective catalytic reduction systems, but most people probably know this as the system that uses AdBlue in their car. And for petrol vehicles, again, which includes hybrids without a plug, 19 out of 90 petrol vehicles produced on-road emissions that were above the current or upcoming lab limits. 2 of these petrol vehicles produced NOx readings that were above the applicable lab limit, and 5 produced carbon monoxide results that were above the lab limits. Interestingly, there were 15 petrol vehicles that produced particle emissions on road that were above the limits applicable to diesel engines. The context there is for particle number regulation, there's a limit for diesel vehicles, but not yet a limit for petrol vehicles. So 15 petrol vehicles exceeded the limit for diesel vehicles. So those results we just covered were the distance-specific results over the whole course of the trip. I'll just keep an eye on the time. i.e. they're the average results across the 93-kilometre trip, which includes urban, rural and motorway driving. What's on the screen now is an example of the second-by-second data that we collect through our portable emissions measurement system. And this is collected for each pollutant for every car that we test. And of the 114 cars we've tested, there's 2 tests, at least 2 tests for every car. What's on the screen here is the time series data for nitric oxide emissions, nitrogen dioxide emissions, and NOx. And again, this is just one example, but this example is useful to demonstrate, I guess, the potential for the data, particularly in, looking at how new vehicles are coming onto the market and how they're entering our fleet, and the effectiveness of new technologies. So I mentioned before that there's AdBlue technology in diesel vehicles. Another technology that's, I guess, relevant and prominent in new diesel vehicles is what's called a diesel particulate filter. Essentially, these are metal filters in the exhaust system that capture particles, and every so often the filter becomes a certain level blocked, and it has to burn off again to do a reset. And this is normal operation for what's called a diesel particulate filter. The trace on the screen shows what is recorded for the NOx emissions when a vehicle does one of these burns, a diesel particulate burn. So you can see about halfway through the trip, the NOx emissions increased while a DPF burn was occurring. It also shows the cold start emissions early on in the test, as well as, I guess, some spikes later in the test as the vehicle is braking and accelerating, comes back through the urban and the rural sections of the test. The next one, again, just keeping on time, I'll quickly cover off one. So this is another example of just a couple of cars and the data that we collect. And I guess I'll highlight this time that my job is to conduct the testing and make sure the results are robust. So this example popped up in the robustness test because they're from 2 similar vehicles. And again, these are the NOx readings in the second-by-second throughout the test. So 2 similar vehicles from the same vehicle manufacturer with similar engines, but they had very different NOx emissions. You can see on the screen the blue results are clearly much higher than the results for the orange vehicle. I guess aside from the cold start where both vehicles had a spike. I guess the important point here is the orange results. That vehicle was fitted with the selective catalytic reduction system that I mentioned before, which uses AdBlue. Most people just use it AdBlue, so I'll just call it the AdBlue system. And again, that system exists in modern diesel vehicles. We're going to see more and more of these over coming years to reduce the tailpipe noxious emissions. The blue vehicle did not have the AdBlue system. So these 2 slides and the 2 examples are really just examples for what the data can be used for. So I didn't design the cars, only the car maker knows the difference between these cars and the way that they operate, the way they did, and whether or not that was normal operation or not. But the message that I want to convey here is that the real-world testing program is collecting a huge amount of data on-road performance and data that is otherwise not available. And this brings me to my final slide. Where can you find the data? So the second-by-second data that we spoke of is not yet publicly available, but the Commonwealth is working towards making this data available on an open access arrangement. So they're looking at including it into an existing platform, perhaps something like the data.gov.au platform. But in any case, I think it's quite exciting that this huge amount of data set will be open access at some point in the near future. While the overall results, so these are the distance-specific results, the average results across the 93-kilometre journey, they are already published publicly at realworld.org.au. And as Nico mentioned before, we've had quite a few stakeholders interested in getting the data in an Excel file, and I'm very happy to share that with people who are interested. And I guess to summarise, what's the real testing program? It's going to test 200 cars over 4 years in real driving conditions and publish those results to empower consumers and provide transparency around the running costs and environmental performance of new vehicles. Thanks again, and I'll throw back to Sabrina.
Thanks, Jason. So now, thanks for giving an excellent overview of the real world testing program. It's all very exciting. Now we'll open the floor for any questions that the attendees may have. I think we'll go to Nico first. There was a question from Dorothy. So New Zealand's latest happens study highlighted diesels as the major source of NO2 emissions. Australia's diesel vehicle standards continue to lag behind Europe, where the Australian's NOx limit is 5 times worse than the Europe, and many premature deaths from traffic emissions could therefore be prevented by tackling the highest emitting diesels. Were you able to estimate PM2.5 and NO2 exposure and associated premature mortality separately for petrol vehicles, heavy and light diesels? Because this important info would help identify and implement the best and most cost-effective ways to protect against harmful pollution.
Yes, thank you, Sabrina. Yeah, and thank you, Dorothy. That's a great question. Actually, we didn't estimate specifically for different fuel types. What we did in our random forest model. So we had 2 inputs. So the chemical transport models, those were not specific models from the center. They were developed by DPI from New South Wales and EPA Victoria, and they shared those results with us. And we combined with the national pollutants inventories, which I would have to check if they have emissions by fuel type. I'm not really sure, but we didn't do the analysis. But it definitely would be something very interesting to sort of disentangle where do most of the emissions come from, and if they come from diesel and there are less diesel vehicles, then that could potentially be a very interesting intervention, especially with the data that Jason is showing.
Thanks, Nico. And Jason, do you have any comments on that? Were you able to find that, like, they were emitting more pollutants with diesel as compared to the other as compared to petrol vehicles?
I think, well, I guess one of the stats that I mentioned before was the number of diesel vehicles that are exceeding the lab limit for NOx. So we have consistently seen, essentially Euro 5 vehicles exceed their noxious limits in real world settings rather than the lab settings. So I think that probably does talk to that quite a bit, yeah.
But also, sorry to interrupt, from the last slide that I showed, from the data that Jason shared, yes. So diesel vehicles tend to have higher NOx emissions than petrol vehicles.
Thanks, Nico and Jason. So just following on the Happin study. So the Happin study revealed a very large burden, and the position statement out of University of Melbourne revealed a significant burden here in Australia in regards to TRAP, fairly in line with other estimates internationally. Anthony was asking Nico, what degree of underestimation of the TRAP harms could have occurred in your study?
Yes, thank you, Anthony. Yeah, that's a very relevant question. So I think that in reality, the Melbourne Uni statement is completely overestimating the actual burden. I don't think it's in line with the international evidence, at least from the analysis that we did. So I think that estimate was around 11,000 deaths per year, based on some estimates, following the estimates from that cohort in New South Wales. So if you look at our study, you can look at some data from in the appendix. I'm just going to see if I can share this quickly. So you have this table A3, where we estimate the annual mortality. This is from all sources, so it's higher than our TRAP estimates across different scenarios. And our highest estimate is using the health risk coefficients from the New Zealand Happins 3.0 cohort, and we get an estimate of 8,700 deaths with the maximum range in the 95% confidence intervals is just below 10,000. So this is from all sources. Now, if we look at TRAP, it's higher than our estimates, but it would be around 6,500 deaths. But we don't really know, so that's why we tested all of this sensitivity analysis, and we don't know the true burden, but I don't think it's as high as this. Populations in New Zealand and Australia are probably very different, and the levels of exposure are also different. And the baseline health conditions are also different. So I'm not sure if I would trust this estimate as much. And probably the estimates that I showed are a bit underestimating the true burden from trap, but it's nowhere close to 10 or 11,000 deaths per year. I don't think so.
Thanks, Nico. And did you compare to other countries where the levels of air pollution is generally lower, like Australia, in addition to New Zealand? Because I saw it.
Yes. So what usually happens in, at least for PM 2.5, is that these beta coefficients, what they are doing is they're capturing the like the slope, so the marginal effects of changes in air pollution, and because of the shape of these curves, when you're in low pollution settings, that slope, that beta coefficient tends to be higher. So that is why you would probably get higher impacts in locations like Australia or New Zealand with let's say, for each unit change in pollution compared to somewhere that is more polluted. Like, let's say I come from Chile, like in Chile, for example.
Thanks, Nico. Just a question for Jason and maybe Sarah. So if the real world emission and lab results to differ as you've shown, so what is done after that to ensure that the information given to consumers reflects the real world emission result? Because I think not all consumers are aware of your publicly available data.
Yep. So that's a really good question, and I guess think of the program as a non-regulatory lever that I guess the government that we can try to pull to empower consumers and inform the market, and I guess let them know what they should expect for their new vehicles. And the closest example I'll give is like ANCAP, where it is a non-regulatory program that publishes safety performance of vehicles to try to, I guess, increase the demand for safety performance. So we use our motoring clubs to proliferate the results for the program to their 9.5 million members. So the program is still very much in its early days. We only started testing in August 2023, but we're hoping that, I guess, as we get more of the market covered and as more people, I guess, are buying vehicles, we've got to remember that only a certain portion of the population buy a new vehicle, and when they do, they perhaps only do it every 3 to 5 years. But that's how we expect to influence the market through the program, by telling consumers what they should expect, and them telling the manufacturers then what they expect from their new vehicles. So, basically stop demand for vehicles that overpromise and underdeliver. That's the easiest way to describe it.
Thanks, Jason. And for Nico, there's a question from Stephen. Again, just comparing to other countries like the Europe. So Australia has higher octane levels in basic petrol than the EU. If so, are PM 2.5 air pollution levels higher too in Australia?
Thanks, Steve. Actually, I'm sorry for my ignorance, but I don't really know. But this could be interesting. I don't know if this would be something that maybe Jason and team could test for petrol vehicles, testing with different octane levels.
So that's a good question. It's a good, I guess, piece for or use for the data. So Australia actually doesn't have generally, Australia's fuel octane levels are certainly lower than Europe. So Europe basic spec is 95 RON, whereas in Australia we have 91. But I think the point about PM is probably still relevant because Europe moved to Euro 16 many years ago, and essentially what that saw was an introduction in new technologies to comply with that RDE test I mentioned off the back of the Volkswagen scandal. So I suspect there will be many new cars in Europe that are fitted with gasoline particulate filters to reduce the particle matter. Is that fair response, Sarah?
Yes, I think so.
Thanks, Sarah. Thanks, Jason. So just looking at the Q&A, I think this might be just our last question. Nico, I saw that you're going to answer Martin's comment live.
Oh, I made a mistake. Sorry, I
Oh,
I didn't know how this works. No, I was
okay.
just wanted to thank Martin and have a look at that paper.
Okay, no worries. And Sarah, Jason, Michelle is just asking about where we can find the information for hybrid testing results. So if you can just provide that link or share it with us with the Center for Safe Air, then we can share it with the attendees.
Yep, just a quick one on Michelle's question. So we haven't actually started testing plug-in hybrids yet. That's the next one for us. So we're hoping to commence that in the next little while, but happy to keep the group updated on when that happens.
Thanks, Jason. So as we conclude today's webinar, I'd like to extend my sincere appreciation to Nico, Jason, and Sarah for sharing their time and insights on this topic. We hope our attendees found the discussion valuable and informative, as I did. Sorry if we did not manage to get through all the questions, but we'll pass them on to the speakers and be in touch with you soon. If you have any further questions or would like additional resources, please don't hesitate to reach out to the Center for Safe Air. We look forward to seeing you at our next webinar. Thank you and have a great day, everyone.
Bye. You.